All right, the correlation between the heights in inches of fathers and the heights in inches of sons, which is on the Y, is 0.89. So what that's telling you is the sun's heights are here, and that is in inches, and the father's heights are on the X. Okay, now the question is, if we take these inches and we convert them to feet, does it change the correlation coefficient? And the answer is no. It doesn't have any effect on it. So it is unchanged. All right, in the following residual plot, consider the point that is indicated by the arrow. Okay, I circled it. Which of the following statements must be true about the individual represented by that point? Well, that point is below the zero line in the residual plot. The zero line is the one that I highlighted in yellow. Okay, so that means that the actual subtracted the predicted is a negative number. That would mean that the actual is smaller than the predicted. So the actual response variable is less than its predicted variable. B. A study of the effects of television measured their reading scores and how many hours of TV each of the 125 grade school children watched per week during the school year. Which variable should go on the horizontal? So the horizontal, okay, that's your x-axis. That's where you put your explanatory variable. So what this study is trying to do is to show that the number of hours watching TV has some sort of influence on reading scores. So your hours of TV, that's your explanatory, and then that would go on the x-axis. So the number of hours of television, because it is the explanatory variable. Okay, the height in feet and the volume in cubic feet of usable lumber of 32 cherry trees are measured by a researcher. The goal is to determine if the volume of usable lumber can be estimated from the height. Okay, in this study, the response variable is, okay, the response is always plotted on the vertical. So our volume is the response variable. Okay, a study is conducted to determine if one can predict the yield. So whatever is getting predicted, that is your response. So the yield, how much crops you get, is being predicted by the amount of fertilizer applied to the soil. So the yield is the response variable. Consider the following scatter plot, which describes the relationship between stopping distance and temperature. So temperature is your explanatory, and stopping distance is your response. All right, so you see when I draw an oval around those dots, the oval is longer in this direction. So this is uphill, which means you have a positive relationship. All right, so we're going to be looking for correlation coefficients that are positive. So I know it can't be D. Okay, this one, the dots aren't super close, but they're not all scattered. All right, so if it was 0.9, these dots would be really close to that dotted green line. So that leaves me with 0.6 as an estimated correlation coefficient. All right, suppose a straight line is fit to data having a response variable y and an explanatory variable x. Predicting values of y values of x outside the range of the observed data is called extrapolation. So for example, if I said the outdoor temperature was, let's say, 90 degrees, okay, that would be way over here. This is outside the range of the data that I collected. So in the previous example, using 90 to predict the stopping distance when it's 90 degrees outside would be an example of extrapolation, because the 90 is doesn't fall between -10 and 40 degrees. So we would get an unreliable prediction. Okay, a linear regression equation was computed to predict the final exam score in a statistics class from the score on the first test. The equation for the least squares regression line was y predicted, so that is the predicted exam score, and x is the score on the first exam. So this equation right here would be the same as the predicted all right, so my predicted final exam score is equal to 10 plus 0.9 times the score on the first exam. Okay, Joe got a 90 on the first exam. So I'm going to take that 90 and I'm going to put it right here and evaluate the equation. So when I do 10 times 0.9 times 90, that's 10 plus 81. And that is 91, which is the predicted final exam score. All right, so a study gathers data on the outside temp during the winter in degrees Fahrenheit in the amount of natural gas a household consumes in cubic feet per day. Call the temperature X and the gas consumption Y. The house is heated with gas, so X helps explain Y. So X is our temperature, that would go on the X axis. Y is our response, which is the vertical axis. Least squares regression line for predicting y from x is given by this equation. Okay, when the temperature goes up 1 degree, what happens to the gas consumption? Well, that is the same as the slope. The slope describes what happens when this increases by 1. What does the gas consumption do? And this tells you that. So as the temperature increases by 1, the gas consumption goes down or decreases 19 cubic feet. So as the temperature goes up 1, the gas consumption goes down by 19 cubic feet. So as the temperature increases by 1, the gas usage goes down by 19 cubic feet. Okay, a study gathers, so it's the same equation, the same study as number 9, where we have the predicted usage is 1344 minus 19 times whatever the cubic or the outside temp is. The y-intercept in this case is the value 1344. It represents the response variable, so in this case, the usage when the outside temperature is 0. So we have 1,344 cubic feet gas is used when the outdoor temperature is 0. So our answer is B. Okay, that's the y-intercept. And in this case, this one makes sense. Okay, when the temperature is 0, it's going to be cold. You're going to be using a lot of gas to warm the home. If it doesn't make sense, then I would look at my answer being possibly C. Okay, y-intercept of the regression line, but it has no practical purpose in the context of this problem. That would be if it was it didn't make sense. Okay, 11 is asking, does there appear to be a relationship between the consumption of artificial sweeteners and headaches? Okay, so if you look at this, for the folks that consumed an artificial sweetener, okay, 80% of those people got a headache. Okay, for the folks that did not consume an artificial sweetener, only 40% got a headache. So you can see that these two rectangles here are not the same size. And when they're not the same size, that's indicating there is an association. So we're looking for the response that says there is an association. A is not an association. B is. C is. D is not. Okay, so let's see what these two say. There is an association between artificial sweetener and headaches because headache occurrences were not the same for those who consumed artificial sweeteners and who didn't. That's true because the boxes are different sizes. So you're looking for boxes that are not the same. And that tells you there's an association. Okay, 12, two students that go to different schools compare the amount of homework each day by the day of the week and asks if there's an association between day of the week and the amount of homework. So you can see in this school, in Lynn's school, these are about the same size. So there's really no association between the day of the week and the amount of homework. Whereas over here at Nate's school, these bars are different sizes for homework. Therefore, there is an association between the day of the week and the amount of homework being assigned. So our solution here is D. Nathan's school has an association. There is an association because the percent of the homework assigned is different for different days. Right? In Lynn's school, there's not an association, okay, because the homework assigned, the percent of homework assigned is the same. So when it's the same, no association. When it's different, association. All right, when you're interpreting a scatter plot, you're mentioning these things: direction, are there any unusual features, the form, the strength, and then what's the context? So we've got a positive direction because it's uphill. Okay, there doesn't seem to be any outliers. Okay, the form, well, it's pretty obvious that's linear. Since those dots are fairly close to that imaginary line, it would be strong. And the context is farm size and cost. So bigger farms cost more. So the response that checks all of those boxes is B. All right, when you have a coefficient of 0.986, that's close to 1. The closer to 1, the stronger these things are. So I'm looking for an uphill, okay, one that looks like a line, and the dots are close to the line, which would be C. All right, student needed a calculator for her stats class. She collected selling price and the number of bids received from eBay on the same model calculator she needs to purchase. The equation for the regression line is given, and so it's 60.386 plus 322 times the number of bids. That's the predicted cost. All right, where X is the number of bids received and Y is the predicted selling price. All right, calculate and interpret the residual for the calculator that received 32 bids and sold for $73. So to get the residual, your residual is equal to the actual price take away the predicted. So right here we did the predicted price by substituting in 32 for the number of bids and evaluating that. So the predicted or the expected price was $70.69. However, the calculator sold for $73. So if we subtract the expected from the actual, we get the residual, which was $2.31. So the actual selling price was $2.31 more than what we expected to pay using the regression equation. Okay, now when you're looking at your choices here, you got to be careful because two of them say that the calculator sold for $2.31 more than expected. Both C and D do that. Now, the way that you determine which one of those is right is the first one, B, was based on a regression line using X being the number of bids, and D says the X value was the selling price. Well, we know that the X value was not the selling price. The X value was the number of bids. So B is our correct answer. Okay, 16, you got 3 residual plots. Which one indicate that a linear regression line is appropriate? Well, this one has a leftover pattern, so that is not good. Okay, and then C has a leftover pattern. B is a random pattern. Okay, random patterns mean the least squares regression line is appropriate. When there's a leftover pattern, not appropriate. So the only one that is where it's appropriate would be B. So 16, the last two, you have leftover patterns. This one is a curve and this one is a wave. Those tell you that the original would not be good to use a least squares regression line. All right, 17. There's a relationship between smoking and lung health. People who smoke tend to have worse lung health than those who don't smoke. What's the explanatory variable? Well, the explanatory variable influences the response. In this case, whether or not you smoke influences your lung health. So our explanatory variable is going to be smoking status, and our response is going to be lung health. All right. The scatter plot displays a roughly linear relationship between the miles run in a practice and the time required to finish a race for a random sample of 25 cross-country runners from a recent meet. The correlation for this relationship is found to be negative 8.89. So that would look something like this. Okay, as race time is the miles in practice increase, your race time decreases. So we're looking to check these things: negative, strong, linear, and then have the context. So the only one that matches all of those things is, looks like, is going to be, I'm looking for strong and negative, strong, negative, linear. So those, and then the context is miles run in practice and the time to finish. So my correct description would be D. All right, many local water companies encourage their customers to use devices that limit water use to help reduce their water bills. Scatterplot and least squares regression line display the relationship between the number of water conservation devices and the monthly water bills for a random selection of 9 homes that receive their water from a local water company. Okay, the equation of the least squares regression line is right here. And this is our correlation. So we've got a strong negative correlation, which means as the number of devices goes up, your water bill goes down, which makes sense. The number, because you're conservation devices, you're conserving water. All right. So, what is the predicted water bill for a home with 3 devices? Is this greater or less than expected? All right. So, the predicted, to get that, we're going to plug in our 3 devices into our prediction equation. So there's our prediction equation, and we're gonna substitute in 3. Right? So we get a predicted value of $23 and 27 cents. All right. So then to get the residual, I take the actual bill. So I go up to the table, and when you have 3 conservation devices, the actual bill is $26. So 26 take away the predicted, and I get a difference of $2.27, which means the actual bill was greater than what we expected by $2.27. Okay, so let's see. D is our solution. Louis is shopping for a used car and collects data on age. So age is your explainer, age and price, and it's a negative relationship because as the car gets older, the price is going to go down. As age increases, price decreases. All right, here, now over here is the residual plot. So for example, this dot right here, its residual is that. Okay, that represents $4,000. Okay, and it's above the 0 line. So this would mean that the actual price was $4,000 greater than the predicted price if we used a line to do that. So we determine whether or not a line is appropriate by looking, does this data look random here? Does the residual look random, or does it look sort of like there's a pattern there? I think there's a pattern, so I'm going to say there is a leftover pattern. And when there's a leftover pattern, that means an LSRL is not appropriate. So another model would be better than using a line. Because there is a leftover pattern, all right, a least squares regression line is not an appropriate model.